Lepo pozdravljeni, začnemo še z zadnjim današnjim delom. Pozdravljamo tudi našega gosta, hello, Daniel, ki prihaja iz skupnega raziskovalnega središča v ISPRI, v okviru Evropske komisije. Predstavil vam bo potresno in energetsko prenovo stavb, to različne raziskovalne projekte, ki imajo, ter tudi dejavnosti tega skupnega raziskovalnega središča. While I'm introducing you, please share your presentation. It will be okay, Daniel?
Yes, can you see my screen already?
Yeah, perfectly. Bi sam povedala, o čem bo govoril, se pravi, predstavil bo različne tehnike potresne in energetske sanacije, da bi na najmanjši invaziven možni način zmanjšali, se pravi, potresno ranljivost stavb ter povečali energetsko učinkovitost. In kot sem že omenila, bo predstavljena tudi primeri eksperimentalnega preizkušanja teh prenov na tem JRC-ju in tudi bo predstavil laboratorij, ker predavatelj je zaposlen na JRC-ju v laboratoriju kot raziskovalec. Je drugače rojen Dunajčan, ki je celoten študij zaključil v Združenem kraljestvu, je potresni inženir z tega področja, ker ima tudi doktorat. In njegovo raziskovalno delo se prepleta predvsem s temi, se pravi, potresnimi utrditvami v kombinaciji z energetsko prenovo ter tudi razvojem celostnega vrednotenja trajnosti, funkcionalnosti in lepote, kar smo danes že večkrat slišali, se pravi, meril novega evropskega Bauhausa. The floor is yours now, Daniel.
Perfect. Thanks a lot, Neva. So yeah, as I was introduced already, I'm Daniel, or also known as Sasha Pohorides from the European Commission Joint Research Center. And my talk today is going to be about integrated seismic and energy retrofitting of buildings with a specific focus on ongoing JRC activities. So before I start, I will give you a quick overview of my talk today. So I'm going to tell you a bit about what the Joint Research Center actually is. I'm going to introduce to you our laboratory, the European Laboratory for Structural Assessment, also known as ELSA. Then I will talk to you quickly about some combined and integrated retrofitting technologies with some multi-criteria assessment of combined retrofitting technologies that we did at the JRC. And then more interestingly, some examples of experimental testing of integrated retrofitting solutions that we did either at the JRC or with partners within the framework of JRC projects. And finally, I'm going to finish with some current activities at ELSA that are buildings currently inside of the lab. So what is the JRC? The JRC is the Joint Research Center of the European Commission. It provides independent, evidence-based knowledge and science supporting EU policies to positively impact society. So our role within the European Commission is to provide science for policymakers. And for that reason, we try to anticipate needs for policymakers, integrate knowledge that exists out there, and have impact actually on the policy cycle. The JRC has multiple sites. So we are in ISPRA, which is the site in Italy. The headquarters are in Brussels, as for most of the European Commission. And we also have other sites in Petten in the Netherlands, in Geel in Belgium, in Karlsruhe in Germany, and in Sevilla in Spain. At our site in ISPRA, we are home to the European Laboratory for Structural Assessment, ELSA. And our laboratory is actually two different laboratories. So it's a research infrastructure that is used to test safe and secure buildings. We have on the one hand the HOP lab, which is a lab for testing materials under high impact loading. And on the other hand, the laboratory that I'm going to talk to you about much more today is the reaction wall, which is a large scale facility in which we can test full scale buildings to earthquake loading. We provide open access to this JRC infrastructure, so there's possibility to come and do tests at our laboratory for universities or for companies. We also provide training to researchers across Europe, so feel free to inquire when we do our trainings. And we provide transnational access through the Horizon Europe ERIS project. I will show you an example of one of the projects in there today. And we also have projects that are inside of the JRC. I will give you some examples of these today as well. And our reaction wall facility that you can see a nice picture here is a very specific and very special facility in Europe. It's the largest reaction wall facility in Europe, the second largest in the world. We can carry out safety assessment of full-scale buildings. It has unique dimensions. So you can see here with the technical side, let's say it's a 16-meter tall, strong wall together with a 4.2 meter deep, strong floor. We have capacity to test on two sides of the wall, so we can carry out experiments on multiple buildings in the same time frame. We can carry out seismic testing in one direction or in two directions. And we can carry out also hybrid testing for larger structures. So for example, when there's bridges, we can test big elements of a bridge, but simulate the rest of it. Also for buildings, we can test, let's say, a part of a building, but simulate the rest of the building through numerical modeling. So we have a lot of expertise on that. Here you can see a bit our lab in action. So when a test starts, we have to first move the building inside of the lab in the right position. And here you see an accelerated test. So our hybrid testing, or pseudodynamic testing as it's called, is actually a slowed down version of an earthquake. We can reproduce the forces, dynamic forces, through our numerical models and then test it. And we go through the whole project cycle. At the end, we also demolish the building and look a bit at construction and demolition waste at the end of the project life cycle. So we really look at the whole project life cycle. And we do this because a lot of the pre-normative testing for the Eurocodes, for instance, is done here. A lot of the, let's say, research that goes into construction and demolition waste regulations is done here. So we really try to influence policymaking through our scientific results. Now to get to the more, let's say, pressing topic of the presentation, combined and integrated retrofitting technologies. I'm going to start with a brief introduction of the motivation and background. I'm sure most of you are familiar with this already if you're listening to this series of lectures. But yeah, as we all know, our cities and buildings in Europe are aging, and about 80% of the EU building stock is over 30 years old. This means that many of our buildings, about 3/4, are deemed energy inefficient. They are responsible for, or the construction and building sector is responsible for, a large proportion of CO2 emissions and a large proportion of EU energy consumption, so up to 40% of EU energy consumption. And at the same time, over 170 million Europeans are potentially exposed to earthquake hazard, which has very often catastrophic consequences if the buildings are not adequately designed or retrofitted. So what we can do for these buildings is that we can either take no action, which obviously leads to bad energy performance and potential losses during an earthquake. We can, and this is something that has been done a lot recently, focus on the energy side and do the energy renovation. However, if you're in an earthquake-prone zone, this alone will not help, and you will actually lose the investment that you made into the energy renovation. So we are trying instead to promote actions that make sure that the building is safe and energy efficient at the same time. This can be done either through, obviously, demolition and reconstruction of a new building to the highest standards, which will give it a good energy efficiency and a good safety, or which might be more, let's say, sustainable from a life cycle analysis perspective. You can carry out integrated seismic and energy retrofitting, ensure that there's a good energy efficiency of the building, and also ensure that it withstands the earthquake in the zone. So what we did at the JRC within the pilot project we built, which was carried out a few years ago, is a multi-criteria assessment of combined retrofitting options. The idea of combined retrofitting is to ensure sustainability and seismic safety. and resilience as such. But we try to, let's say, cut it out into 6 different criteria that we used for assessment. So one is, let's say, the reduction in losses from seismic events. The other one is the reduction of impact to the environment. The reduced labor time of combining the retrofitting compared to carrying out the seismic and the energy retrofitting separately. We also looked, of course, at the enhancement of heating energy efficiency in buildings, the improvement of the resilience of our diverse building stock, and the cost effectiveness of carrying out these 2 interventions either together or in an integrated fashion. We categorized possible combined retrofitting options into 4 categories, starting from exoskeletons, interventions on the building envelope, replacement of the building envelope, or retrofitting of the roofs and the floors of a building. I'm going to focus today on envelope interventions because these are things that we actually also tested in our lab. But this doesn't mean that the other types of retrofitting options are not equally valid. From our evaluation, envelope interventions proposed so far have a lot of benefits in terms of structural safety, sustainability, and energy efficiency point of view, and they're usually the most cost effective. So focusing on the interventions on existing building envelopes, when you think about a large proportion of the European building stock, you will have especially buildings built between the 1950s and 1980s in Europe. They will be reinforced concrete buildings with masonry infill walls. These infill walls do contribute to the strength and stiffness of a reinforced concrete building. However, they can also be the source of severe damage to the load-carrying elements, because usually they are not actually considered in the design of the building. This can cause global collapse or local collapse. And you have some images here from the L'Aquila earthquake where you have some kind of pancake failures or failures of the envelope. At the same time, from the energy perspective, they're also responsible for a lot of the energy losses through thermal transmittance and air infiltration through the wall, because typically in the 50s or 60s especially, there was no thermal insulation placed on these walls. Here are some examples of interventions that can be done for the existing building envelopes that have been proposed in the scientific literature. I will talk about some of these cases more specifically when I talk about the JRC projects. So there's a possibility, for example, to combine textile reinforced mortars with thermal insulation. You can use CLT panels as a retrofitting option. You can also look only at the windows and apply a new fenestration surface, and at the same time apply a steel frame around the window to strengthen the walls. Or you can look at different precast solutions, precast integrated retrofitting panels. There have been a lot of proposals lately on this topic. The benefits of these interventions is that they can be really applicable to many types of buildings. So whether you look at infilled reinforced concrete buildings, masonry buildings, or steel buildings with infills, they're usually not so invasive to the building because you just need to modify, let's say, the outer envelope or sometimes also the inner one. The relocation of residents might not even be needed because you can work from the outside. And the business downtime is also low in the case if the intervention is done only from the outside. And on the other hand, if you look at prefabricated or modular elements, you can also carry out these interventions in a much faster way than if you look at exoskeletons or things like that. The issue in some cases, though, is that it modifies the appearance of a building facade. This might be something that you actually want if you want to do also an architectural upgrade of the building. But in some cases, it's not possible. So if you're looking at the historical center of a European city, very often it's not possible to completely modify the appearance of the building facade. So you need to rethink how you can do such an intervention. You also need to look at foundations and existing frame members, because maybe you improve the envelope, but then you increase the shear forces that the building has to sustain, which then maybe the reinforced concrete frame cannot sustain. And if you're looking at low quality substrate or one-sided applications, the efficiency of these interventions might not be so high. So I'm going to focus now a bit on some experimental tests that we carried out at the JRC on these specific integrated retrofitting solutions on the building envelope. One of the first projects we did on this topic was the project iResist Plus, innovative seismic plus energy retrofitting of the existing building stock. The idea of it is to combine thermal insulation with textile reinforced mortar. So you see here the textile being applied on this little video. This could be, in our case, it was a basalt textile, but it could be, of course, glass or carbon textile as well. Then you apply some mortar on it, and you have the thermal insulation inside of this reinforcement. And when we tested this on a full-scale building that you can see here in our laboratory, we found that with this TRM plus thermal insulation retrofit, you can get a very large improvement in the capacity, an improvement in the stiffness, and you can test the same building, because we do pseudodynamic testing, to earthquakes. So we don't just look at let's say the envelope curve, but we also look for the same earthquake. So the building that was not retrofitted could sustain an earthquake, which was about a third in terms of the intensity than the building that was tested with the textile reinforced mortar plus thermal insulation. What we also did on this building is that we tested the energy performance of the building in terms of blower door tests. So this tests how much air infiltration actually happens in the building at different levels of damage or at different levels of cracking. So we first tested it to low damage with the seismic testing. Then we repeated the blower door test at medium damage and at high damage as well. Then we didn't do the blower door test anymore because we had actually gaps and damage that would be needed to completely rebuild the masonry infills. And what we found is that you have the curve in red, which is the non-retrofitted building, and the curve in green, which is the retrofitted building. And for the same level of drift, so the same level of displacement in the building, you have much higher air infiltration losses in the non-retrofitted building. So even if you go up to 0.4% drift, which is a very large drift, you have, let's say, nearly the same performance as the building in its existing state. While with the non-retrofitted building, when you increase the damage, you have more and more losses for air infiltration. Of course, if you're at the high damage, this doesn't really matter because you have to rebuild the walls anyway. But if you're at the low damage, you might have some cracks that you don't actually repair. So if you're looking at maybe this first dot around 0.15% drift, this might be a situation where you don't actually need to repair the building from a structural perspective, but you have increased air infiltration, so increased energy demand afterwards. We published recently a study on this to look also at the effect on the heating energy demand, and the effect is very large. We have done some other tests on precast panels that have a very similar, let's say, idea, which also uses carbon textile or textile reinforced mortar, let's say, in this case with carbon textiles. But instead, for the thermal insulation, we're using capillary tube system. The capillary tube systems is maybe something that you're familiar with when you look at modern houses that have underfloor heating. So they're small tubes for which hot water or cold water can be passed in order to heat or cool the floors. They have also been proposed for walls. And in our case, we try to use them together with the textile reinforced mortar in a precast panel that can be modular, so you can attach the different panels to each other, and like this heat or cool the walls, and at the same time provide additional stiffness and strength to the walls with the carbon textile. We have done this in collaboration with COSIT, which is an construction engineering research institute in Korea. And we have done some tests first on individual frames. So you can see here, we did comparisons of our retrofitting system, which is the one with basalt, TRM, and thermal insulation, and the retrofitting system with the precast panels. And when you look at the cyclic response of these, so pushing and pulling these frames laterally, we found that actually you can achieve exactly the same response, or more or less exactly the same response, whether you use textile reinforced mortar or using these precast panels. So this was, let's say, a proof of the concept. But more interestingly, we then also went to, let's say, the building scale. We tested buildings with a similar geometry to the one that we tested at ELSA, but this time on a shaking table in Korea. due to the shaking table dimensions, we could only test the building in one, let's say, with a 1x1 frame instead of the 1x2 frame that we had in our lab. But the general dimensions are quite similar. And we tested it with the retrofit with the precast panels on the left and the retrofit with the TRM plus thermal insulation. And I'll show you now a video of the tests, let's say the final test of each of these buildings at 150% of the design earthquake with a PGA of 0.72 G. And you can see the existing building, non-retrofitted, has full collapse of the masonry infill walls, while the two retrofitted buildings have, let's say, much lower intensity of floor acceleration. The building responds in a much stiffer way, and you have absolutely no damage at the end when you look at the building. So let's say this kind of envelope retrofitting systems have been evaluated now in our lab at the reaction wall facility, but also in the shaking table facility in Korea in this collaborative partnership between JRC and COSIT. And COSIT has also done some evaluations of the thermal performance. Don't have any images on that, but also the thermal performance of the buildings has significantly improved. So now I might move a bit away from the combined retrofitting, but look at some seismic retrofitting activities that we are currently carrying out at our laboratory. So as I mentioned to you before, our laboratory has, on the one hand, let's say, internal projects. So the project that I've shown you so far, the IRISIS Plus project, is a JRC internal project, let's say, with the aim of exploring these new technologies and seeing how these technologies actually can perform in an anticipatory way. So to see really how this can influence policymaking in the future. And we have actually had some impact as well in making sure that future renovation policies also include the idea of combined and integrated renovating and not just having the energy renovation alone. But we also carry out activities that are in the framework of Horizon Europe, and more specifically in the IRIS project. So the IRIS project is the Engineering Research Infrastructures for European Synergies project. There's multiple laboratories across Europe that are participating in this project. The current IRIS project lasts until next year, and we have already carried out quite a lot of testing of different buildings within this framework. One that I will talk about right now is the Revolt project. So this is a building that is currently inside of our laboratory, and testing will start actually within the next 2 weeks. So it's really, let's say, the current project that we're working on. The project is called Revolt, which stands for Response Evaluation of Masonry Vaults under Pseudodynamic Loadings. As it's part of the IRIS project, it's actually a user group external to the JRC that has made the proposal and has been responsible, let's say, for the scientific development of the project in terms of the specimen, so in terms of the piece of building that you can see here right now. It's a collaboration between the University of Genova in Italy, the University of Minho in Portugal, and Cadacol, which is a company that produces materials. There's also collaboration with the University of Oxford on it. You see here some name of people that are responsible for it, and at the same time, our JRC team at the ELSA laboratory is responsible for carrying out the design, making sure we can carry out the design according to the specifications and the needs of the user group. You can see here, let's say, a first rendering of the building, but I will tell you a bit more in detail what it is. So this is a type of structure that you might be familiar with also in Slovenia, but in most of Southern Europe, or most of Europe actually, we have churches that have vaults inside of them. So typically you have maybe 3 or 4 vaults, as you can see here on the left side. And in our lab, as we can carry out hybrid testing where we simulate the full structure but only test a part of the structure, what we did is extract this vault with the correct boundary conditions. So you have the internal wall on this side and the external wall on the other side, which are built from stone masonry. The vault in the middle, which is, let's say, the most interesting part, a brick masonry cross vault. And at the top, we can apply the loading, the seismic loading, according to the specifications of the user. You can see the dimensions here. So the wall is nearly 7 meters tall. The external one is about 5.6 meters tall. Each of the arches are around 3 meters in width. So it's really a very large and full scale part of the structure. And we have some tie rods, as you would have probably in a church nowadays that has been already retrofitted maybe some decades ago. And this represents, let's say, the current structure. Here you see some examples of seismic damage on this kind of structure. So as you see, let's say, most of the cracking would happen, let's say, along the diagonal of the bolts, and that's something that we want to simulate in our earthquake testing. Here you can see the construction of the specimen. As this specimen was built from stone masonry, so sedimentary limestone was used for building the walls and the columns, and then bricks to build the vaults. We had to actually construct the specimen inside of the laboratory. At the beginning, I showed you a video of a building being moved inside of the lab. Usually we build the building outside and then we move it inside of the lab. But this building, as it would probably collapse by moving it inside of the lab, had to actually be being built inside of our laboratory. So you can see like the work of the stone masons and now the work of the masons to build the vault. Obviously accelerated. This took maybe around a month and a half to complete the full construction. There was some plastering applied on top. So now you don't see the nice stone masonry anymore. And this is the final, let's say, view of the building now. Currently, we applied a speckled pattern. So the same building is now in the lab with a lot of little black dots because we want to use digital image correlation. So we use 2 cameras in stereo vision in order to have, let's say, full information about the 3D movements of every single point of the vault and every single point of the wall. So the idea of these kind of tests that we carry out in our lab is really to collect as much data as possible, to publish this data in an open access way afterwards, so that it can be used for maybe improving construction, improving numerical modeling, improving future testing. So when we have a test like this, we try to get as much data and information as possible. And why I'm presenting this right now when I talk about retrofitting is that there's actually 2 phases of testing. So the current vault is going to be tested now in the next weeks and next month in the unstrengthened configuration. So the building as it is, or the part of the church as it is, will be tested up to moderate damage. So we will test it on the one hand with some cyclic testing, but on the other hand also with some pseudodynamic or hybrid seismic testing, where we want to go up to a level of damage that is still easily repairable. So we don't want to have the risk of the vault being too damaged. And then in a second phase, early next year, we will have the company coming in and renovating, or in this case, actually repairing and retrofitting the vault with steel reinforced grout, SRG. You can see some examples on previous tests that they did on a smaller scale. So you have similar to the textile reinforced mortar, but in this case, a sheet made from steel fibers that is being applied on top of some mortar, and then you have a second layer of mortar applied on top of it. And this will be a mortar that obviously is also compatible with the kind of masonry substrate that the vault is made from. So the whole testing will then be resumed. We will test the building to the same levels of earthquakes, and ideally, if the hypothesis is correct that the retrofitting works well, we will also test the building to higher levels of seismicity, higher levels of seismic damage at the end, until a state close to collapse. We cannot go to full collapse, of course, in our lab, because we cannot have, let's say, the the whole vault falling down on all our instrumentation and on our strong floor, but we monitor the test, and with our hybrid testing method where we can go slowly, we go until a level where, let's say, the capacity of the building starts to reduce too much, and then we will stop the test. So this is a typical kind of retrofitting test that we do in our lab, that we test first the non-retrofitted and then the retrofitted building. So I come now to the general conclusions of my talk. So as I showed you at the beginning, our building stock is aging, and a large part of Europe and a large part of our building stock is in need for seismic and energy retrofitting. We have done in our pilot project, we built an assessment of all possible combined and integrated seismic and energy retrofitting techniques that have been tested so far by scientists or companies. There's, of course, hopefully room for development for future technologies. And we have categorized them into 4 main types: exoskeletons, interventions on the existing envelope, replacement of the existing envelope, and interventions on the horizontal elements. I have focused my talk on the interventions on the existing envelopes with some examples of testing at ELSA and testing in Korea in combination with COSID. In general, what we found is that there's further development and experimental research still required, because many of the assessed technologies are actually still in a conceptual stage or tested at a small scale. And there's really need for more validation and testing and more experimental data. The experimental data from the tests that we have carried out at ELSA and in Korea are available in open access journal articles, and also the data is available for those who require it for numerical modeling. So the idea is really that we want to advance this field of research, and we want to promote these combined or integrated retrofitting schemes for future renovation of buildings in Europe. You will find a lot of information in relevant reports from the JRC or in our journal articles. So on the left hand, these 2 yellow reports, but there's a whole series of other reports within the same project from the pilot project Rebuild on integrated techniques for the seismic strengthening and energy efficiency of existing buildings. If you search for Rebuild with the 2 E's online, you will also find our website, where there's a lot of the data that we have used for carrying out assessments on the EU scale. So we have had a look at seismic risk and energy efficiency on the EU scale. And we have made an online tool available to everybody. So if you go to the Rebuild website, you find that. You can also find the JRC technical report on the IRISIS Plus project. So that's a project on the testing of a typical masonry infilled reinforced concrete building in our laboratory with thermal insulation and textile reinforced mortars. So you find some numerical simulation and impact assessment in this report, but there's also been recently published some journal articles about the test results with this technology, but also with some other technologies tested. And similarly, the tests that we have carried out together with our Korean colleagues have been published in journal articles in engineering structure. So if you want to find out more, please have a look at these articles. I provided a list of references here. So if I understood correctly, you will have the access to the PDF of these slides, so you can have a look at the references in more detail if you're curious about it. And with that, I would like to thank you and give you also the opportunity for some questions, hopefully, and remarks. And I open the floor for questions and remarks.
Thank you for the excellent presentation. There are 2 compliments in chat. Just a moment, if you can read. Multi-criteria decision-making study. It is one question, I think. Are the outcomes of a multi-criteria? Can you see it?
Yes.
Yeah.
Are the outcomes of a multi-criteria? Okay, well, that's a very pertinent question, actually, because obviously what we tried is to create a framework rather than look actually at let's say individual projects. We wanted to build a framework in which we can do this multi-criteria decision-making process. So we have done this first for residential buildings, and let's say I showed you one slide with some visuals about like which are, let's say, more sustainable or which ones are more energy efficient, but we have actually also a full report on that. So it's one of the reports that I showed before, where we give some results, and the results we have done not for a case study building that would be, let's say, the building of a building owner, but for more generic, let's say, building and generic series of buildings in order to have an idea of what this means on a general level. We have then tried to use this multi-criteria decision-making process for school buildings in Italy. We've recently published a paper on that actually with a visiting researcher from Padova, where we looked at school buildings. And there we saw that this multi-criteria decision-making process is applicable also to school buildings. And we have some results for the full building stock of school buildings in Italy. But again, of course, this doesn't go to the level of individual buildings. The thinking process, though, could be applied maybe not by the building owner, but by the engineers that are carrying out the renovation process. And then this is something very important. Every building is slightly different. Every building has its own characteristics. The location is different. So even when you look at, what seismic retrofitting options or what energy retrofitting options you have, you cannot come with a general idea and say, using TRM and thermal insulation is always the best. It depends fully on the building that you're looking at. And you can use the thinking process of the multi-criteria decision-making process, but you cannot apply this in general to any kind of building. You always need to do the evaluation of the specific building, location, because maybe in some countries, certain materials have a lower life cycle impact. So maybe, getting basalt fibers might be something that has no transportation impact when you do it in Italy. But if you do it in Lithuania, you might need to actually ship this product from Spain all the way to Lithuania, which increases the life cycle impact. So you cannot generalize, but you can use the framework.
Še kakšno vprašanje? Is there any more questions? Sorry.
You can also see on our website, on the website of the Rebuild, maybe I can add it to the chart. You can see, let's say, some analysis that we did on the full European building stock until the NUTS-free regions. So these are the small, let's say, local regions. Maybe in Italy it would be the provinces. Maybe in Slovenia you have some kind of smaller than regions as well. And you can see the results of how much building renovation can be beneficial on this general scheme. So not for the individual building, but how much building renovation can be beneficial if you do only seismic renovation, if you do only energy renovation, or if you do the combined or integrated one. So this can be something that maybe doesn't help the individual building owner to make a decision, but it can help public administration. It can help engineering companies to decide what direction to invest in more. I will try to add this to the chat as well.
Then I have one question. Do you work also, what are the costs of such reinforcements?
Well, we try to look at costs again in quite a generic way. So we try to see a bit for, let's say, case study buildings. We try to calculate some costs in specific locations. And then we used something that is the European Construction Cost Index. So it's a construction cost index that gives you, let's say, how much construction costs more in different EU member states. And we multiplied it by that, let's say, for the different member states. So it's something, again, very generic and gives you some ideas of maybe textile reinforced mortar is maybe cheaper than an exoskeleton, but you cannot really have the answer for a specific building again. But yeah, our idea is not to inform on the building level, but more on the general overview. And also, construction costs are very fluctuating. So we saw already after COVID and after the war in Ukraine how much construction costs increased due to the material costs. If we produce a new report every year, we will have completely different results, maybe for different kinds of materials, also steel and aluminium imports or things like that, that have increased a lot, make maybe now a steel exoskeleton much more costly than building something out of concrete. So it's our idea is always to provide frameworks and ways of thinking rather than individual results.
Thanks a lot. Is there any questions or anyhow, thanks for your lecture, for your time, for your collaboration, and we are looking forward to further collaboration. Thank you a lot.
Thanks for having me, and have a nice rest of your day.
The same, yeah. Bye.
Bye-bye.